Okay. Yeah, you guys can see it?
Yes.
Okay, nice. So let me speed run through this. Let's go back to chapter 5, okay? The reference, okay? Reference is these two articles. Basically, I just walked through the first one. The second one is a little intimidating. I can't do it right now. Requires too much math, so I can come back later. You can see I have this work in progress label here. Yeah, let's go over some facts about BLS curve. So this curve was designed to be a pairing-friendly curve. Okay, so of course we can have like many elliptic curves, but to be pairing-friendly, you have to like specifically construct for it. Okay, so this curve is like artificially constructed curve just to do pairing. Okay, so so why do we want it to be pairing friendly? Because in the last step of graph 16, you have this verifier step. You have to compute pairing 4 times, and then just like check the equality. So yeah, we want to minimize this step. So we have to use a pairing friendly curve. So the naming of this curve, BLS 12-381. So 12 means the embedding degree is 12. We're gonna talk about what is embedding degree later. 381 means the number of bits, like the size of the field modulus Q is 381. Okay. So some basic facts about this curve. Y squared equals xq plus 4. Recall that usually we work with BN 128 curve. That curve is like plus 3, so this one is plus 4, like subtle difference. So in the standard of the curve, you have you just have this capital X. This is a constant that defined in the standard. Note that this X is not that X in the equation. So they are different, okay? So this capital X, so it is just like a constant defined by some trusted third party, So based on this capital X, you can compute for the field modulus Q. So this field modulus is not like coming from nowhere. Okay, so so this one is like derived. Also, the subgroup size R is derived. So this R, what I mean by subgroup is think about that G1, G2 in the PYECC library. Okay, so both G1 and G2 are subgroup, and both of them having a size of R. So this value is also derived from a predefined constant. Okay. So a pretty confusing topic is field extension. So the 12 in this name, the 12 in this name means the degree of field extension. So for FQ, the finite field FQ, we can only define G1 group from here. So there is no way to define G2 group. Therefore, we have to do a field extension until we reach this FQ12. Okay, so this is still confusing notation, but don't worry, we're gonna cover it slowly. So for constructing, yeah, let's just stop worrying about this Q12. Let's say how do we construct FQ2 from FQ? Okay, so this is a simpler example. We can do some basic algebra, right? So say finite field of modulus Q, it is like Z mod QZ, right? So you have Q elements from 0 to Q minus 1. And then we define FQ2 in this way. So we define it as a polynomial, degree 1 polynomial, where all the coefficients A0 and A1 are from the field FQ. Okay. So equivalently, you know that so for a polynomial, you always have that one x squared, x cubed, that series, okay? So that part is predefined. So we can just simplify this polynomial into a coordinate representation, right? So a0, a1, it always refers to a0 plus a1x. These are equivalent definitions. So for constructing a field, we have to define two operations. Because, yeah, recall that a field is just a commutative ring where all non-zero elements have inverse. Okay, so since ring have two binary operations, we have to define the same for a field, and then for addition, this is pretty easy. So you just do AB plus CD. You can do some basic algebra like convert this to back to the polynomial representation, and then do some basic algebra here. Okay, this is pretty easy. But for the multiplication case, it is subtle, because we have something like BD x squared that we cannot handle, because in the definition we did not define like what is x squared. Therefore, we have to convert this x squared to some number, right? So for this case, the rule is we define x squared plus 1 equals 0. So this is the thing, like we are extending the field R based on this rule. So we are adding a new rule, because this like x squared plus 1 does not exist in R, right? So this one is a new rule that we added into here. So we can substitute x squared with -1. So it is pretty easy to see that we can just substitute -1 here. So this term becomes minus BD, and you can do some algebra and define this multiplication. So, yeah, so this is well defined now. What we did is extending R to C. Maybe you can see that this thing is just the I, the well-known I, okay? So I squared equals -1. So we are adding this rule into some original field, and then we are extending the field because we are adding a new rule into it. So that's the idea of field extension, okay? Yeah, that's a pretty simplified example, but I find it quite easy to understand. Yeah, so I put it here. General criteria for the rule, for this rule, okay? So our case, the degree was degree k polynomial. I'm a little confused here. I think it's k minus 1, but you get the idea, okay? So the rule, oh, no. Oh, this is correct. So extension degree right now is 2. So we are adding a degree 2 polynomials here. Okay, yeah, that makes sense. So in our case, R to C, extension degree is 2. Then the rule is degree 2 polynomials, yes. And the rule must be irreducible. So x squared plus 1 is irreducible in R, because we cannot further factor this polynomial into like x plus something times x minus something, but we can do that in C, right? So we can factor this as x plus I times x minus I equals 0, okay? So that makes sense. Yeah, that's a criteria for the rule. And this is a fact that C is like the ultimate form for this type of extension, because you cannot further extend it, because there is no more irreducible polynomial in C. That is saying you cannot just find something like that, like x squared plus some constant equals 0. all the thing with that form will be reducible because of fundamental theorem of algebra, okay? Like a variation of that theorem. So you can always factor things over C, so there's no way to extend it. What I'm saying here, in contrast, when K irreducible polynomial. Yeah, I probably made mistake here. I think this is FQK or something, right? We can extend FQ to FQK. Yeah, I think I missed something here. Yeah, I'll fix later. So in a general case, we can find the irreducible in finite field and then extend that base field to FQK, right? So the form is this long polynomial. So the basic idea is the same as the C case, but this one is more general. And it is pretty hard to say like which irreducible polynomial I can find, but yeah, I'm just saying it is possible to do that. And for our case, we only care about FQ12, yeah, because we need to construct a G2 subgroup from it, okay? So in BLS 12381, there are two curves. So don't assume this one is the only curve, because from this curve we can only construct G1. We actually need another group to construct G2. Okay. So we were saying this one should be FQ12, but why is FQ2 here? Because we can use that twist, like stack-stick twist. Like I don't understand how it works, but yeah. So with that technique, we can transfer FQ12 to FQ2, so the computation will be easier, as you can imagine. Okay. So a word about the curve order. So there's a theorem, pretty famous theorem called Hess's lemma. Oh no, I mean Hess's theorem. Say capital N is the number on curve over a finite field of modulus Q. And then you have this bound. So the absolute value of this expression is bounded by 2 times square root Q. You can just expand this to solve for N, and then eventually you will see N is bounded by Q plus 1 minus some square root and Q plus 1 plus some square root. So when Q is large, you can see 1 is like useless. So we can ignore that, right? So when Q gets large, square root Q is relatively small. So we can just assume this N, which is the curve order, is bounded by some margin of Q, right? So N will be like similar to Q, but there will be a difference. So the curve order and field modulus, generally, they are not the same, but they are pretty close. Yeah. So for like further study, you can watch this video. Yeah, pretty nice. I watched the first half of it. Yeah, pretty nice introduction. So the conclusion here is the curve order of the first curve. Oh, I should say E prime here. Okay, E prime. The curve order of EFQ is kind of like close to Q, and E prime FQ2 is close to Q squared. Okay. So that's for the curve order. You can see the first curve is much smaller than the second one. So now we are constructing G1 and G2. They are the subgroups of the curves. Recall that in bilinear pairing, we need a G1, G2 group. They map to a, like we do pairing parentheses G1, comma G2. We map that thing to a point on the target group. In general, this should be like G12 group here. Okay, so G1 and G2, they must have the same order R. We call that R is a derived value from a constant capital X we just mentioned about. Okay, so this value is derived and it is a prime. So it is always a prime. And G1 and G2 must have the same order, but there is something you should worry about is if you only have E of FQ, there is no way to generate G2. So the only thing you can do here is generating G1 because EFQ, it only has one large subgroup of order n. So that's the only thing, okay? You just grab that thing and call it G1 and we are done here, but we need something else to define G2, okay? So we have to extend the EFQ to EFQK, do the field extension we just talked about just now, okay? So why we want to do that? Because in E of FQK, there are many subgroups of order R, and we are going to pick a special one from it. So the special one has a property saying is a trace equals 0. This one I don't quite understand yet. It's pretty involved math, so I gonna come back. But for now, you just think about we already construct G1, and from there we use that curve and we extend it to a higher curve, right? And then we find all the subgroups in it with order R, and there is one special point. That special point is a special subgroup. The special property of it is trace equals 0. Why is that? I don't know. But this is G2, okay? So this is how G2 was constructed. So the K in EFQK is called embedding degree. You're gonna see this word a lot in literature, okay? So you can prove that E of FQ12 is good enough to define G2. So this is like the bare minimum for defining G2. So we stop it here, okay? A fact is G1 and G2, they share the same identity element, the point at infinity O. Okay, so at this stage we construct G1 and we use some cryptic math and constructed G2. We're gonna come back to this math. I can't handle it right now. So we have G1 and G2. Now we can do pairing. Yeah, we come to the most difficult part. This one, I think I got the idea, but this one is still work in progress, okay? So the idea is if, we were extending E of FQ to FQ12, but you can imagine the computation here is pretty complicated, okay? So for example, if we want to use this in production, we have to minimize that because we're gonna wrap that G2 into pairing again. So that is computing G2 is already complicated, and then you wrap it in a pairing, just make things more complicated. Okay, so we have to simplify this part. So how it's done is called like sextic twist, something like that. You can Google that. It's pretty. I don't think I understand the math behind it. Okay, so this twist, the main idea is just it can somehow convert this large finite field into a simpler one somehow, and you can find a new subgroup that is isomorphic to G2, so you can do all the computation in the new subgroup instead of like doing over this monster. Okay, that's the idea. How it works, I don't know. I'm gonna figure this out later. Yeah, this is the idea. So at this stage, we have G1, we have G2 from the new elliptic curve, the one out like the one after reduction. So we have a G1, a new G2. The new expression of this curve is just times 1 plus I on this constant term. Yeah, like you have to figure out this part in order to derive this equation. But since I didn't figure out this part, yeah, you can just accept it as a fact for now, like this one, okay? In G1 group, a point is a pair of integers. This is pretty easy to understand. So this is just like an elliptic curve on 2D surface. You just graph it and you have a x coordinate and y coordinate, okay? For G2, it is more complicated. Why? Because you can see we introduce I here. Therefore, the coordinates become a complex number. Remember that for each complex number, we have a real part and imaginary part. So to represent G2, we have to use 4 coordinates. So this one is just think about this one. This one is like integer. But this one is like a plus bi and c plus di. So the x coordinate is a complex number and y coordinate is also a complex number, which makes the thing like represented by 4 numbers, but G1 is just 2. Yeah, this one was pretty hard to understand. I think I kind of understand the ideas now, but the math behind it is still complicated. So that explains why G1 has 2 coordinates, but G2 has 4 coordinates. Yeah, because it represents complex numbers. Yeah, that's the short answer. Okay. So for pairing, we still treat it as black box because I need to figure out the math behind. To do pairing, for now we still use as a black box. Okay, so we denote pairing as E. The domain is G1 cross G2. This is a direct product of the 2 points. So for example, like P, we pick P from G1 and Q from G2. So P is a G1 point, Q is a G2 point. We can say, oh, E parentheses PQ. This is a pairing of those 2 points. So just remember, when you do pairing, one of the component must be G1 point and the other must be G2 point. Yeah, that's everything you need to know for now. So usually we call this pairing bilinear pairing. So why is that? Because it has some nice property. So it is linear on both sides. That's why it's called bilinear. So for example, if we have linearity on the right, this Q plus R, you can just say, oh, we can do pairing first and then the second pairing and then multiply them. Yeah, same for the first component. Okay. So it's called bilinear because we have 2 linear properties here. A fun fact here is if you combine 1 and 2, you can derive for an interesting fact. So in general, the proof looks like this. So you say bracket A times P. So what is this? This is just scalar multiplication. So it is like P plus P plus P for A times. Okay. So this one same Q plus Q plus Q for B times. Okay. So first you can factor this A. You can take this out as the exponent. Because we are applying like this number 2 property for A times. Yeah, so we got this, okay? So similarly, we can factor this B out and take it to the exponent by using property 1 for B times, okay? And then the funny thing here is you see you can just take this A down to the other component here. So A was on the left, now it is on the right. Yeah, this is pretty interesting. And you can bring this B back to the other. So pairing of AP BQ is the same as BP AQ. So pretty interesting property here. Okay. So the insight here is, so why we do define pairing? Because recall that over a elliptic curve over finite field, we only have one operation, which is addition. So the scalar multiplication is just a variation of that. Okay. So pairing basically acts as the multiplication of a G1 point and G2 point, but you cannot say that like rigorously. Okay. So this is just like a easier way to understand it. But in math, this is of course wrong because like they are not even in the same dimension. So you cannot multiply, quote unquote, multiply that. And another word about the embedding degree. So yeah, this one I think I'm still a little bit confused on why is that, but there is an algorithm to compute k. So this embedding degree k is just the smallest integer. So this smallest is very interesting property because, yeah, so look at this. So it must satisfy r divides q to the k minus 1, but it has to be the smallest integer. So how do we do that? Yeah, we can just use a for loop, start with k equals 0, and then just increment it, okay? Just compute. Because we already know r, and then we can, yeah, of course, we already know q, so we can just say, oh, q to the 0, q to the 1, q to the 2, and then blah, blah, blah. Iterate through all the possibilities, and then you can find, oh, the smallest integer in our case for a given r and q, the smallest integer is 12. That's the embedding degree of BLS curve. Also, it is the embedding degree of BN128 curve. Same thing. Okay. That was pretty much the theory behind it. So we gonna talk about one application about BLS. So I chose BLS signature. This is very fun because I didn't know that BLS curve and BLS signature, they represent different people names, you know. So the L is the same person, but B, I think this B is Dan Bunet. And the B and S in the BLS curve, I don't remember their names, but B and S, like they are different. So this is a different B, different S, but the same L. Yeah, pretty interesting fact. BLS signature is still like a typical digital signature algorithm. Okay, so we're gonna talk about it. So first thing is the key generation part. How it works? First, you pick a random number between 1 and R1. So this is wrong. This is the unit group of Z mod RZ. The unit group. I should put a star here. A star here. Okay. So there is no 0. So it's the unit group of Z mod RZ. You generate a random number. You keep it secret. This is your private key. How to compute the public key? You just multiply secret key. I mean scalar multiply, okay, by G1, where G1 is the generator of the G1 subgroup. For this one, I think every non-identity element in G1 should be a generator. Why? Because that corollary of Lagrange theorem. I think so because it says if G1 has prime order, then every element other than the identity, which is a capital O point at infinity. So anything other than that should be a generator. Okay, so you scalar multiply your secret key onto that G1 point. So this one is the exactly the same as ECDSA, which is used in Ethereum. This one is pretty common. So why I label is G1 point here, because I want you guys to know it's pretty easy to mess up. Yeah, so everything we work with, they are either a integer over a finite field, or a G1 point, or a G2 point. We don't work with anything else. So it's better to just like label everything. And when you actually code it in Python, for example, yeah, you can just put this G1 into the variable name so you can distinguish everything. Yeah, this is like just my experience. Public key is pretty safe. We can publish over internet. Internet is an example of dangerous, untrusted channel. Okay, so we can publish it publicly. Why? Because it is protected by ECDLP. We talked about this last time. So ECDLP, the discrete logarithm problem on the curve, given sk times g1 is almost impossible to compute this sk. Okay, that's the ECDLP. We have private key and public key. Recall that in digital signature, we sign a message with a private key, and we let other people verify our message verify our signature using the public key, because that's the only thing they got. This private key is your secret. Yeah. So in the sending phase, first we have to map a message M. So this is our secret message. We have to hash it to a point on G2. So how is that hash done? First you hash it, very likely you should choose something like zk-friendly hash, okay? There are a few choices, and then you choose one of the hash function. You compute it to an integer modulo q, so gmod qz or fq, okay? You map it to some large integer, and then you just use that as the x coordinate, and you set y coordinate to 0, maybe, I think, yeah. You use that point and check if that point is actually on curve. If not, you have to increment that message +1 and try again, and just loop it, iterate all the possibility until you have something on the curve. Then you can say, oh, I have a point on G2. So I can just multiply G2 and get this capital HM. So this is the hash. So when you send the message, you are not directly sending a message M, because remember, we either work with G1 point or G2 point at this moment. So we have to multiply HM, which is a G2 point. And then when you multiply G2 point with a scalar, it's still on G2. So this is still a G2 point, okay? We call that public key G1 point, signature G2 point. Sounds very good. We have some something to work for pairing. Okay, so in the verification phase, we have message. Even message. I think this is wrong as well. I think this is HM, because the message is a secret. How can it be given, right? I'm gonna take a look at this later. I think it's wrong. It should be HM, something like that. Okay, so some representation of M, and then a signature sigma public key. The verifier has all the information, and then the verifier verifies if the secret key is corresponding to the public key. Okay, so how it's done? It is done by pairing. We can just do pairing once. First, no, I mean we do the comparison once. We have to compute two pairings. The first one is G1 and sigma. The second one is public key and HM. So after we compute these two pairings, we compare the equality. If it's equal, then the signature is valid. It is coming from this user. Okay. So it is just pairing in PyECC library. in this BIS 12 underscore 381 library. Okay. So how do we know if the thing is correct? We can just derive the formula a bit using the bilinear property. Okay. So start with pk hm. We have the expression for pk. Pk equals secret key times g1. So remember, this is a public key. Also, this is a g1 point. And hm, recall that hm equals to, we just hash it and then increment it, and then times g2. Yeah, multiply that by g2. So this is a g2 point. So we have g1 point, g2 point. We can do pairing on that, well defined. Okay. So recall that we can use a property like like by many times, and then get this. We can factor this sk to the exponent, and then we can just drop this sk back to the other position. Yeah, you see that this is pretty funny, but you have to do this in 2 steps, because if you got like from here to here, then you skip 1 step, right? But here you actually apply the first property, and then you apply the second property. So you have to write this step out. Okay. So property 1 and then property 2. You see the effect is we change the position of sk, and this sk times h1, we call that this is just the sigma, the digital signature. So this is a g2 point. G1 is obviously G1 point. Okay, so this one equals to e to the, of G1 sigma, G1 point, G2 point, well-defined pair. So this is the correctness proof. So what's so good about this signature scheme? This pairing-based signature, it is because has a aggregation property. So what does it mean? So verifying a single M. So a single message M signed by n parties, it requires only 2 pairings. So recall that you probably thought like between 2 people, we have to do 2 pairings already, right? So between like n people, there should be 2n pairings, but no, because it has aggregation property. We only need 2 pairings if n parties, like many people, sign the same message, or if they are n parties signing a different n messages, we only need n plus 1 pairing. I think this one is a little bit more complicated to prove, so I have a example for the first property. Okay. So here's the proof. So consider sigma digital signature sigma aggregated equals sigma 1 plus sigma 2 plus sigma n. Okay, so this is a G2 point. Public key, we can also aggregate it. Just take the sum of all the public keys, and then you get a G1 point. And you can prove this fact. So this is the pairing of G1, comma, sigma aggregated. This one is equal to public key aggregated, comma, HM. So yeah, you can just substitute this long expression here and then prove this property. So this is called the aggregation property of the BIS signature scheme. And you can see basically we have n parties and n signatures and public keys, but in the end, we only do pairing once. So this is pretty efficient. Okay, that's all the info for today. So for the readings, we mentioned this already. So pairing for beginners. This is a very nice book, like around probably 150 pages. Yeah, a little bit long, but very approachable. You can read this in a week, I think. Pretty nice details, the math details behind pairings. Also, I need to go back to this article. I think it's a little bit hard for me right now. I'm gonna go back to this article. Okay. Okay, so That's the all the info for today. Any questions? Wow. Oh, that was a lot. That was a lot of info for me. For my tiny brain, it was a lot of info. Let me see the question. So, wow, there are so many questions. Yeah, I didn't read your question because I have that issue because I was sharing the whole screen. Yes, yes, please ask.
I think the website has some issues when we are sharing. But my question is, if we choose like say smaller r,
Mm,
could we just simply keep that? We don't need to do the extension of the field. We can still use the original field to have two
okay,
sub
okay,
that
okay.
be.
Uh, so first, you are not able to choose a small r because r
That's
is
why we need
derived.
to do the extension for the field because
Oh,
uh,
mm,
we only have one subgroup that is larger enough
y-
with degree r.
I think first r is derived from a given parameter capital like the capital X, right?
Oh,
So
sorry, I cannot hear anything. That's weird.
can't
Let me
hear
stop
anything. I
sharing.
can. Okay. Okay, I said first that R is derived from the capital X, which is a given parameter, right? So why is that X so large? Because security issues, right? Uh, like in the standard, they chose this X must come from like many concerns that have worked out in like like in the past. There will be security issues if you choose like small parameters. I'm pretty sure that's the reason. But if you ask me like what attack can, can I do, I don't know right now. Yeah, I gonna come back to this part later. I think it deserves more research, obviously. Uh, okay, guys, I gonna go because I have 20 more minutes before my Open Zeppelin interview. If you have more questions, please just ask me in Discord. I think I gonna clear my room a little bit. Okay.
Thank you. Good luck
Okay.
in your interview.
Thank you. Thank you. Okay. I will see you guys next week. I will be here for sure. Okay. Next week we can actually go to some ZK problem. So I'm pretty done with the theory